Hey everyone, this is Brian. Welcome to the very last lecture video for CSC 143. Congratulations on making it this far. I hope you've enjoyed the class so far. Before we get started on today's video, which is going to be a pretty chill and relaxed lecture about the applications of data structures, I do want to remind you that the course evaluations are out now. I understand that the online learning format can be pretty challenging. It's definitely been kind of difficult for me to form meaningful relationships with all of you as students, knowing that a lot of the learning that we're doing here is asynchronous. So I do want to get your feedback into how you thought this class was run, what you think we could do to improve this course, and just general feedback and comments you have about your experience. That feedback means a lot to me, and I'm going to take it and try to make the course better in the future for the students to come. And again, I really thank you for your participation and commitment to this class. I think it's really wonderful that you've made it to this point, and I really think that you can take the content that you learned today and from the last several weeks into the classes and whatever careers you choose to pursue that will take advantage of this computer science degree. So please do fill out that form. Let me know what you think, and then enjoy this final long lecture video. Hey everyone, this is Brian. Welcome to another video lecture for CSC 143. Now that we've gone through all the major data structures of computer science, leading from the primitive array all the way up to the graph, I want to walk you through some examples of how these data structures are used in the real world. By the end of this lecture, I'd like you to have some better insight onto how you evaluate the problems you're trying to solve and fit in the data structures you're trying to use into these certain kinds of applications. Let's go ahead and dive in. And I'll start out with this big question of what is the best data structure? If I were to hold this lecture in class, what most students tend to converge on is the HashMap. It's got those nice properties like O of 1 lookup, O of 1 insertion, O of 1 removal. And then some students will also group around the array and the array list, because I think it's relatively easy to understand compared to these other structures. Generally speaking though, I don't think there is a best data structure. I think it depends on the circumstances of the problem you're trying to solve. We've seen how these structures will all have certain trade-offs, such as their big O performance, or big O space consumption. And depending on the problem you're trying to solve, some data structures may be a better fit than others. Let's start out with a trip back through time, back to 1973 when the C programming language first came out, which is actually still being used today, and go over how this primitive array sort of spawned all these other structures based on its certain challenges and applications. Back in C, there was no such thing as like a Java-style string. Instead, all we had was a character array. Let's call that my buffer. And inside that character array, I would simply store the characters I needed to compose the string that I was trying to build. So here, the character array myBuff is the string hello, but the string is not really a Java string. It's not really an instance of a class. It's really just a primitive array of a bunch of characters. And these characters include not only the characters of the string itself, so HELLO, but also an additional character, this null terminator character, that indicates the very end of the string. Back in C land, we didn't have object instances, we didn't have methods like length, so the best we could do was just end the string with a null byte to indicate that this was the very end of the array. So before there were strings, there were character arrays, and these were extremely efficient. They had zero overhead. There was no additional method references that needed to be stored next to the string, because it was just a series of bytes back to back, and that was it. You may have seen something like this before. This is the ASCII lookup table, and it's a mapping that we humans have designed to associate some number, like 72, with a given letter in the English alphabet and all these other special characters. So the letter capital H is associated with the number 72, so we will store the number 72 within the slot index 0 of the character array. One character takes up 1 byte, which is 8 bits, of course. 2 to the 8, which is the number of possible combinations that we can store within a single byte, gives us 256 ASCII characters. And if we look down the entire table, we can see all sorts of characters like all these special characters, punctuation, space, numbers, capital letters, lowercase letters, and so forth. You can find these kinds of tables online. This is one that I just found off a Google search. And it's a pretty useful reference sometimes when you are examining these raw strings as the underlying bytes. This null terminator here, this null terminator is the 0 value. So if you have a string composed of characters and you see a 0 byte inside, that is a byte that has all the bits set to 0, that would be a null terminator character. There isn't really an equivalent of a null terminator character in pen and paper land in real life, because we would just stop writing. But in computers, there's no indication of where the writing has stopped, because there's going to be more bytes beyond this string, so we use this null terminator to indicate that this is the very end. One unfortunate consequence of this sort of primitive level of object storage is that we depend a lot on raw pointers. And we've discussed in the past how raw pointers are dangerous, because the memory outside of the string buffer itself is unprotected. In fact, we get universal read and write access to every single byte in memory when we run a program. Off by one errors are going to overwrite important memory. For example, let's suppose this was our stack, and the myBuff reference, well, not reference, pointer, because we don't have references, we have pointers. The myBuffer was located here in the stack, and it had 512 bytes involved, so it went from this location at the bottom all the way up to this endpoint, where we would probably store the null terminator. Around this buffer, we see some other important things like the local variables, the stack frame pointer, the return address, and C is not going to prevent us from writing beyond our buffer accidentally. In Java, we've seen how the array list will throw an exception when you try to read or write to an array index that doesn't exist. C does not have that luxury. C is not going to prevent you from making these kinds of mistakes. There is no overhead involved. All you get is a location in memory that represents the start of the character array. So if you accidentally write beyond the end of that character array, bad things can happen. One great advantage, though, of having these primitive arrays is that you get really fast performance. And part of that has to do with something called caching. Arrays are fast. They're really fast. They sacrifice complexity for speed, and they get us that magical O(1) indexing. Part of this reason is because inside memory, whenever we load arrays for usage on the processor, maybe we're reading or writing bytes, during the transfer of data from main memory all the way up to the processor, we are going to cache certain bits of the bytes, the data that we read, such that they're more easily accessible as we get closer and closer to the processor. So let's suppose for a moment that this buffer hello was stored across some set of bytes in the RAM, and the CPU needed to read this buffer, maybe because it's trying to print out to the console. When it reads the buffer from main memory, it's actually going to grab a whole chunk of bytes, a large surface area. And then as we get closer and closer to the processor and these caches get smaller and smaller, we're going to narrow down the target of bytes that we're looking for until eventually we will reach the register level, which is the fastest accessible memory to the CPU. And there we'll probably load in the bytes from 0 to 5 here into a register and print them out. But during that process, we will have also loaded those bytes nearby into these different caching layers. And the closer caching layers that are next to the CPU are going to be easier to access for the CPU than these other bytes down here in main memory. So by nature of us scooping up a big bucket of bytes and bringing that bucket closer to the CPU, it's easier for us to read nearby bytes because we've already scooped up such a big bucket of bytes. And these will be loaded up prematurely into the cache. We've talked about this trade-off between speed and storage before, and the size of the cache shrinks as we get faster and faster memory. So if RAM in this old computer is 32 megabytes, we can have cache that's smaller and smaller leading up to the CPU. And intuitively, we can think of this as if we have several grains of sand where each grain represents a single byte, to search through all those grains of sand, it costs less and less time if we have less and less sand to look through. So if we have different layers of cache that get smaller and smaller as they reach the CPU, we can more optimally search the cache to find the bytes that we're actually looking for. The nature of this means we are going to have bigger blocks of memory that are slower, that are further away from the processor, and the caches get faster and faster, but also smaller and smaller as we get closer to the processor. The different layers of caches are going to balance the speed and size requirements. And these contiguous data arrays are going to be very easy to cache, because if I'm scooping up a big bucket of sand, that's going to very likely include the entire array, and that entire array will be somehow stored and perhaps truncated into these smaller and smaller caches. Because I took out an entire scoop of bytes all at once, then what's very likely to happen is that the other bytes within the array are going to be stored nearby in these other caches. That means I don't have to go back down to RAM, the slowest bit of memory, to go look up other parts of the structure, because it's very likely to already be within the cache. Let's zoom out a little bit and talk about the big idea behind caching to make it a more clear picture of what's going on. As memory is read, we're going to copy large nearby contiguous blocks at once into the cache. Because arrays are by nature contiguous, they're very cache friendly. Let's suppose that on this right here, this column, this was our main memory, our RAM, and this center square here is our cache, and our processor is somewhere up here. If my buffer is stored contiguously, block by block, and I'm trying to look up index 2 inside my buffer, then what's going to happen is when I read that buffer, the entire nearby space of bytes is also going to be copied into the cache. For linked lists, this is not so efficient. Because we store linked lists separately, node by node, and each node is stored in its own location, such as this 4-element linked list, it's not necessarily ideal for us to load in all the nearby bytes when we're trying to cache nearby memory. If we try to look up the 4th element of this linked list, this purple element here, and we just finished reading the 3rd element of the linked list, this blue element here, having preloaded all the nearby bytes of the blue element is not going to help us locate the purple element. The consequence of this is that despite linked list having similar performance elements to the array, that is, we can iterate over the entire list in O of n time, and we can look at the different elements in O of 1 time if we have a reference to those elements already, it's not necessarily so fast to perform the iteration because it requires quite a bit of jumping around in memory to go load the nearby bytes that are relevant, which are readily available if we had used an array, but are not so readily available if we are using a linked list, because scooping up a whole bunch of bytes at once into our cache does not help us in the circumstance where all the elements are stored separately. One of the readings I had to do about linked lists was the trade-off between storing all these separate elements and their overhead versus just using something like an array list. Not only are linked lists cache unfriendly, but they incur certain overhead. They have the object overhead of having an additional header and method references for every node involved, as well as allocation overhead. Every insertion requires scanning the entire heap for another free space that I can instantiate a new list node for. In these graphs on the right side here, you see how for the linked lists, which are represented in blue lines, the number of elements, as the number of elements grows, so does the number of bytes, because each element is going to have to consume some degree of overhead to store its class references. For the array list, it doesn't grow nearly as fast, because the array list is just backed by a primitive array. The outcome of this is, arguably, linked lists are not so useful in Java. Because in a lot of circumstances, the array list is going to do the same thing that the linked list does. The expansion process is not terribly costly, and over time, as the number of elements grows, we don't have nearly as much growth in terms of usage space as we see with the linked list. There's a funny tweet here from this man Joshua Bloke, who says, does anyone actually use linked list? I wrote it and I never use it. So there is kind of this question of what's the point of us learning linked list if there's not really that many use cases, if the array list kind of outperforms it every time? Well, linked list does have its uses. Within the operating system, linked lists are excellent for connecting these processes that are stored across different spots inside memory. They are naturally excellent for connecting a sequence of objects that are by nature separately stored. So if I have different processes living in different locations in memory, and I would like to walk all those processes, it's a pretty natural representation to want to compose all these processes together as a linked list and have one process lead to the next, lead to the next, and so forth. It doesn't matter where the processes are, so long as I can walk every process at some point. The heap is also something we can represent using a linked list by chaining together free nodes and used nodes. Remember that the heap is the space where all objects live, and every time we construct a new object, we have to find a free spot within the heap, allocate that spot for that object, and then mark it as used. We can kind of imagine the heap like a street of houses and empty lots. The houses represent objects that are using memory in the heap, and the empty lots represents free spaces. So anytime somebody wants to move in and buy a house that consumes one lot or several lots, if they're constructing a mansion, they're going to have to go walk down the entire street, potentially, to go find a free spot that is available for their house. Very similarly, with the heap structure underlying in Java, the free and consumed spaces will be chained together using a linked list, so that the memory allocator can quickly walk the different gaps of the heap and go find a spot without having to go walk every single byte within the heap. This is kind of like in real life if you started at the first house and you skipped to the next house. You didn't have to walk past the shrubs and the ferns and stuff. You just jumped to the next house. It's quite a bit faster than having to walk every single byte within the heap to go find a free space. Speaking of the operating system, we can also imagine processes as being trees. Every OS process can spawn child processes, and in turn, they may spawn child processes of their own. Each process is going to have its own main thread and memory. For example, when I run IntelliJ, and then I run a test suite inside IntelliJ, we can think of that test suite process, that Java process that runs, as being a child of the IntelliJ process, because the IntelliJ process produced that Java process. Two sort of funny things about processes: parents may terminate their children, and parents may abandon their children. It's possible for IntelliJ to start running a Java program, and for me to close IntelliJ, and that Java program to continue running in the background. That is sort of like orphaning a process, where a parent dies and the child process continues living. I bring this up because I think it's kind of funny. If you take a systems and architecture course, you're going to be learning more about processes and the life cycle of a process. And as part of this research and learning, you're going to be Googling things like parent kill child process, and it looks very suspect when you apply it to search results. There are many more practical applications of trees in the real world, and one of my favorites is trees as websites. Whenever you open a website in a web browser, what you're really seeing is a rendered interpretation of an HTML tree structure. HTML stands for Hypertext Markup Language, and it's a form of XML that describes a tree of elements, such that each element has a certain meaning in the context of the page when it gets rendered. On the right-hand side here, this is the Google homepage, and I'm using the Firefox developer tools to inspect the content, the underlying source code of the Google logo. And what we see with the Google logo is that it's defined by this image tag, img. It has a source URL that locates the image itself, and this image tag is a leaf node among a very long path of nodes leading up to the root node, which is this starting HTML tag. And what the clever thing about HTML does is that it uses the path from the root node, the root HTML node, all the way down to this leaf node, the image, to describe the formatting and semantics of what the image should be. For example, there's a center tag on the way between HTML and image, and that could be used to center the image itself. There's also some other kinds of tags here, such as this body tag or this div ID viewport tag that could have other kinds of meaning and apply certain sort of styles or semantics to the image itself. Nodes may have any number of children to any depth. Nodes can be parents of their own type, and the path to the leaf from the root node gives context to the leaf itself. A pretty clever thing about this strategy is it allows for reusability and extensibility. If I define a certain set of nodes in my tree as being meaningful in a certain way, such as a bold tag, which makes content bold, or an anchor tag, which makes content linked to another location, then I can reuse those tree nodes in several locations within the tree to provide bold text or an anchor to several different leaf nodes within the tree. In the case of making a bold link, for example, I could surround a block of text with a bold tag and then an anchor tag, or I could do it in the other way around. I could surround it with an anchor tag and then a bold tag. So long as the path from the root node, the HTML node, all the way down to the link itself provides the meaning necessary for the element to have a purpose, then those tags will have that intended effect. And we'll be able to reuse those tags wherever we'd like to reuse that purpose. Another compelling application of trees is with languages. We can describe the English language as being a tree. Nodes are entities like subject, object, or verb, and leaves are the words themselves. The feelings of kindness and gentleness, which I had entertained but a few moments before, gave place to hellish rage and gnashing of teeth. We can break down this long sentence into all of its discrete parts, such as the noun phrase and the verb phrase itself, which is a recursive sentence. It includes another sentence that has its own noun phrase and verb phrase, which continues down this tree path until we finally reach the end of the sentence. And we can break down every single word's purpose by where it belongs in the tree's hierarchy. English itself is a recursive language. We're allowed to embed sentences within sentences. Verb phrases can have verb phrases, etc. Sentences can contain more sentences and so forth recursively, pretty much forever until you run out of breath. And what's really special about applying trees to language definitions is that we can discover how so many languages, human languages that is, are recursive in this fashion. If you look at virtually any modern language in English, you're going to see how there's some sort of recursive structure involved, where you can form complex sentences based on the building blocks of the language itself, like the basic sentence, which is just a noun phrase and a verb phrase. In contrast, there's other languages that you might see in programming, like a regular expression, for example, that's much simpler. We're not allowed to necessarily build the same kind of complex objects and sentence diagrams that we see with a human language. And the human mind is very good at breaking down these sentences as they are heard and interpreted them, or is very good at interpreting them in a way that has meaning, such that we don't even think about it consciously when we do this. When I read the sentence aloud, we don't consciously think, oh, this is the noun phrase and this is the verb phrase. Instead, our minds are just very good at processing this tree structure automatically and implicitly. Speaking more about programming languages as trees, we can break down programming languages, including Java, in a similar way. We can think of a statement as being composed of expressions, such as the statement A equals B plus C times D. The expressions themselves are composed of operators like plus and operands like B and C. And those operands themselves may be statements, such as a nested expression. A equals B plus C times D. We could treat C times D itself as its own expression. When the language gets broken down into actual code that gets executed on the machine, the compiler is going to have to take the step of analyzing the individual expressions and tokens inside the language and breaking down their intended purpose and building a tree hierarchy, just like that English sentence we saw, to discover the underlying intent of every single expression or sub-expression inside the overall statement. For example, C times D itself is a standalone expression. B plus C times D is another standalone expression, but we could say that C times D itself is a recursive expression, because B plus C times D is dependent on what the result of C times D itself is. And then finally, when I've figured out what that expression is, I store it in a value like A. What you're seeing here is something called the Chomsky hierarchy of languages. And if you ever take a natural language processing course or a linguistics course, you're probably going to read about this at some point, where we'll see how we can describe more advanced languages and more simple languages by a certain set of what are called production rules, which allow for productions, that is, certain kinds of sentences, to be composed of certain structures. And the more complex the language we get, or actually it's more complex on the way up here, type 0 is the most complex, the more complex languages we get, the more sophisticated our production rules can be. In the simplest case, we have something called a regular language, which simply says that every character can be defined by a character and a successive character. So kind of like a linked list. And regular expressions are this. They are a series of productions where each node inside the language tree can be defined by child nodes, but those child nodes must be succeeded by something. It can be sort of compressed into a linear structure. As we get more complicated, we're going to see that we can form more arbitrary language types that involve things like context sensitivity, where a given sentence can have sophisticated meaning based on sentences nearby. If I give you a sentence that has pronouns, for example, the boy ran to pet the dog, he almost got bitten in the process. You can tell that he refers to the boy and not the dog, because that's how we refer to boys in general, or humans in general, right? And without that context, that first sentence, it can be difficult to discern what the pronoun necessarily refers to. If I just say he got bitten in the process, you might kind of intuitively understand that there was a man who was bitten, but you don't know what did the biting, or what this man was, or if it was a child, or if it was an adult, or something like that. So as we get more advanced, and we get to something more human level, for example, these rules get more and more complicated, and the computation time it takes to understand these languages themselves, the kinds of machines we need, get more complicated as well. This is part of the reason why natural language processing is so complicated. It's why Alexa and Siri and Google Assistant still aren't very good at conversing with you naturally beyond maybe one sentence or two sentences. Those kinds of platforms don't have the complexity to understand this kind of recursion to a meaningful degree, or do something like pronoun resolution to a meaningful amount of accuracy. Trees as file systems. This is something that you see every day. Every time you store a file in a set of folders, then that file is like a leaf node, and the route that is from your disk root directory all the way up to that file is represented by the folders themselves. Directories are the parent nodes. They can also be leaf nodes technically if they are the last node within the path. It's an empty directory, and the files can be treated as the leaf nodes at the very bottom. Git, when you use it, is also very tree-like. Every time you make a commit, it has a parent node or a parent commit attached to it, and the chain of commits merged together essentially represents your project as a whole. There's some special kinds of commits that we'll see, like merge commits, that enable the commit to sort of have two children at once, or sorry, two parents at once. So it's more like a graph structure, but what tends to happen is you're going to have a linear chain of commits on any given branch, and it's kind of like a tree in how the branches diverge off from each other based on certain shared commit parents. Speaking of graphs, let's talk about networking. The internet is composed of several devices and routers, and we can treat the entire internet hierarchy as a graph itself. We can think of endpoint devices like your phone, your laptop, whatever's connected, as a sort of leaf node on the graph, a sort of tree leaf. And the middle nodes, the parent nodes, are the routers that determine the one-hop pathing that gets you from one location to another location. So maybe I have my desktop machine plugged into the wall, it's hooked up to the router, which is then hooked up to higher and higher level routers up to my ISP, and this ISP itself is responsible for doing the exchanging of the data across the cloud and from across continents. Eventually it boils back down to the physical wire, and the physical wire sends the bytes to my computer, and my computer in the computer knows how to display google.com or something like that. If we zoom out into the real world, you can treat this entire structure as a graph. If we think of the route that gets you google.com on your phone from Google's servers that has all these intermediate nodes in between, these intermediate routers that are hosted by your internet service provider or by Google itself that are going to bridge the gap between their servers and your device. Here's perhaps a more refined example where we see there are nodes located in like New York or in London or in Tokyo. And if I'm trying to access some Japanese anime, for example, that's located on some Tokyo server, I might get that data through channels that bridge across certain kinds of nodes. Maybe this blue node here represents a node that bridges North America with Asia. And it's required that all my data pipes through this node at some point. Of course, there's going to be certain extra things like added costs, latency, disconnections. Maybe this bridge from these two nodes that are represented by the dashed line represents a failed severed connection. And one of the really tough things that your internet service provider has to do and figure out for you is how to form these connections on the fly. Typically what will happen is each node inside the graph is sort of responsible for its immediate neighbors, and it knows generally which direction it needs to route traffic to in order to reach a given destination. Every node sort of has this implicit awareness of which way to go to reach a certain location. And as we get closer and closer to these child or leaf nodes, these nodes are more specific and have a deeper understanding of the specific locations that data needs to be routed to, this neighborhood or this zip code, that these higher level nodes don't really think about as much because all they have to do is move traffic into the proper direction. Now, in real life, we've talked about how graphs also can be used to model the world. The maps model, the maps that we use in real life to navigate model the real world as graphs of sorts. Destinations can be thought of as nodes. Buildings can be thought of as nodes. Every street address is a node. Streets themselves are edges, where we walk or we drive on streets, and the cost of traveling each edge is typically the time or maybe the gas it takes to traverse across the edge itself. When it comes to finding routes from one location to another, for example, on the right side here, I have a Google Maps view of how I can get from Microsoft headquarters all the way up to North Seattle College. Google Maps is underneath using something like Dijkstra's algorithm, but it's going to be a bit smarter about just using Dijkstra's algorithm than what we've learned about in class. And in fact, it's probably using a special variant of Dijkstra's called A star. A star is Dijkstra's algorithm on steroids. The way it works is it's going to encourage directions searching within the graph in a way that optimizes finding the ideal outcome and avoids wasting time by going down into other directions. What it's going to do is it's going to use certain kinds of heuristics, like airplane distance to the end location, to encourage the searching algorithm itself to look that way first before it goes and looks in other directions. For example, here, if I were to fly a plane from Microsoft headquarters to North Seattle College, where there's no traffic and no streets and I can go anywhere, I would probably just take this diagonal route. But because I can't quite do that, in real life I have to cross the 520 bridge, what the Google Maps algorithm is going to do is it's going to try and make its way towards this diagonal, but once it realizes it can't cross this water, it's going to take the next best nearby route to eventually converge back to the location it intends to go. What it's not going to do is it's going to be discouraged to go down into locations that are not really relevant. For example, coming all the way down here to Mercer Island or down to Tacoma is not really useful for the purposes of getting to North Seattle College. Not that to say that this may not come in use at some point. If the roads are all blocked, or maybe there's a ton of traffic, then Google will consider this route. But to optimize the execution time of the algorithm itself, it'll try to find a route based on cheap heuristics like airplane distance, such that it doesn't have to do this excess searching if it doesn't need to. Let's talk about artificial intelligence. We can use state graphs to describe the world that an artificial intelligence sees and the kinds of actions it can take to update its own state and the world around it. Remember that state is like the variable values inside an object instance. When an object instance fields are modified, then that object instance's state has been changed. The observed world for an AI, the state that the AI lives in, can be treated as individual graph nodes, and then the edges from one state to another, these transitions, are like actions of a given robot, where that AI chooses to move from one state to the next. Take a look at this Pac-Man graph here. Pac-Man starts in a 3x3 grid on the lower left, and all these cells currently have dots. If Pac-Man moves to the right, then the AI's observation of the world has now updated to where Pac-Man is one cell to the right, and the dot to the right immediately of Pac-Man has been consumed. Then if Pac-Man goes further to the right, Pac-Man consumes the third dot on the bottommost row, and once again the world state has been updated. As we go back and forth between the possible actions that Pac-Man can take, we see how the observed world state updates and transitions between these different kinds of graph nodes. In these three states shown at the bottom here, we see how Pac-Man can simply go back and forth along the bottom row without ever leaving this local area of state. If we were trying to build an AI that solved the Pac-Man game, that decided to optimally chew up all the dots and find the fastest way to clear the board, then we can use those graph search algorithms that we learned in class. Graph search is going to allow these sorts of AIs to find paths leading up to goals. Remember that path method that you wrote for Project 3? Well, that path method could be applied to a tree structure that describes the possible states and transitions that an AI could take to update its world state. Suppose that Pac-Man starts in the lower left with a full grid, and our goal is to clear the entire board. Every single action that we take, whether to go north or go east or something like that, represents a possible edge inside of our tree, and we would like to find the state that has all the dots consumed. That would be our winning state, and we want to get there as fast as possible. Using those algorithms like Dijkstra's, we can find the path across all those state transitions, those state actions that get us from one state to another, until we finally reach the goal in the fastest path. In this little diagram here, this robot is thinking about how it can grab the apple on the tree by jumping a certain degree and a certain amount, and maybe one thing it evaluates is how it does not fall into this gap. The robot can sort of guess if I jump this much high, if I jump at this speed, at this angle, it might fall into the gap if it does one way, but it might grab the apple if it does another way. And these kinds of actions are sort of like these edges in this graph where the state that the robot wants to get to is getting the apple and then getting back to the ground, and avoid the state where it falls into the pit. As an aside, I want to quickly talk about the distinction between AI and machine learning. Contrary to what the media believes and what you might hear a lot, AI and machine learnings are two different things. They are not necessarily interchangeable. AI is about teaching computers to act rationally in a modeled world to achieve goals. Check out this Super Mario World AI, where Mario is mapping out the possible moves and actions to stomp on these Koopas and hopefully get him to the end of the level. Machine learning is about teaching computers to make observations about the world. Here is a machine learning algorithm to identify cats, dogs, ducks, and other animals in pictures. And we see how, rather than thinking about what actions the character or robot itself can take, the machine learning model is more concerned about classifying items given the observations that it sees. Machine learning and AI can coexist, but they're not necessarily synonymous. They solve two different kinds of problems. We can use them together, though, to build very advanced robotics that can adapt to the world around them using machine learning models and decide how to climb a staircase, and then use artificial intelligence to traverse the world around it and support the actions that lead them to eventual goals. Maybe this dog robot is trying to get up to the highest floor in the building, then it can use machine learning to identify things that look like stairs, and then the AI can convince the robot to walk up the stairs because that brings it further to its intended goal. More on machine learning. Fundamental in machine learning are vectors and matrices, things you'll learn about in calculus or linear algebra, which are maybe the requirements for this class, so you've probably heard of these already. And this big idea is that we're going to model complex information as a vector or matrix of integers. We can use things like point or point3D, which we've seen in class, arrays and two-dimensional arrays. Oftentimes, the position of a vector and the proximity to other vectors indicate how those two things are semantically related. kind of like hashing in that we can translate uh, meaning into a set of numbers without the randomness. So we do want these vectors to be predictable in a certain way. Take a look at this diagram shown here, where we have several words and the different kinds of vectors they may represent. For example, let's say the Rome vector starts from the origin point leading up to the bottom right somewhere, and the woman vector leads from the bottom, the origin, all the way up to the top, near the top of the graph. And when we compare the vectors from the origin point of this graph to the word against the vectors from the origin point to other words that are nearby, we can see how we can sort of represent this word cloud as having words that are similar to one another based on the grouping of the words themselves. Maybe man is associated with king or woman is associated with queen, and their semantic similarity is represented by how mathematically close together these vectors are. Another way we can think about representing real-world data and intent in mathematical format is maybe considering this set of handwritten digits. One challenge that machine learning algorithms try to solve is something like input interpretation. How do we translate written text into digital form? And we can compress this digital input data into these 2D matrices where every value in the matrix represents a certain weight, perhaps the darkness in which the cell has been colored in. And our machine learning algorithms can then look at these matrices and think about the kinds of properties that they have in order to decide what kind of numbers are being written. For example, check out this 8 character that's represented in this 8 by 8 matrix of values of darkness. One heuristic we could use to distinguish the 8 from something like the 9 is perhaps the number of islands that are present in the 8 character, where we see there are 2 islands because there's 2 circles, whereas with the 9, there's only 1 island. Or maybe this is actually a 7, I don't know. In any case, the algorithm is going to be programmed to figure out these kinds of heuristics and distinctions to understand this 2-dimensional number representation of what otherwise is a very human-like input that somebody sees and interprets in the real world. Once we have these sort of digitized representations, these numerical representations of this kind of data that we want to classify, we perform these sort of regressions, like a linear regression, any sort of statistical analysis on the data to understand what the data itself is meant to represent. You've probably seen a linear regression before. It's a formula to decide what the line of best fit is for a set of plots on a graph, and maybe you can use this data to extrapolate more information on the future of where the data is going to go. On the right here, in this box, we see an example of something called k-means clustering. And a clustering algorithm is going to try and find partitions in an n-dimensional graph that best distinguish the individual data points being shown. So, for example, we only see a 2-dimensional graph here, but we could have any number of dimensions of data that we are acting on. Properties such as maybe how many islands are there inside the drawing here? How many cells are filled in overall? How many curves are there? Does it look like the bottom cells are filled or the top cells are filled? And based on those attributes, we can divvy up the dimensional data into segments, into partitions that best represent the distinguished sets of values, so that when we start to retrieve new data that we haven't seen before, novel information, we can simply assign it a classification based on which partition that data lands in. Going even deeper, neural nets are perhaps the big hot thing these days, where we use graphs, the same graphs that we've been learning about, to interpret data and come up with conclusions in a very sophisticated way. Neural nets are graphs that transform data repeatedly until it becomes useful. And we train it on larger and larger data sets, and we use a procedure called gradient descent in order to apply certain weights to graph nodes that interpret the data that arrives to produce meaningful outputs in this final output layer that dictates the decisions that are being made by the neural net. Now, neural nets are a bit beyond my understanding. You'll probably need to take a machine learning class if you want to know more about how these work, but they are kind of magical in how they can mathematically over time pick up interesting properties about the kinds of data input that we get and produce meaningful results on the way out. Decision trees are another form of machine learning pattern where we can find meaningful ways to divide up data based on certain kinds of conditions. Maybe this is a decision tree about how much your daily insurance cost, or your monthly insurance premium is, and that tends to be a function of how high of a risk you are as an individual or the asset you're trying to insure. Perhaps you are a new driver, you're young, you just got your license. Chances are your insurance is going to cost a lot. If you've been driving a very long time, if you've never been in an accident, your insurance is probably going to be a bit cheaper. And what insurance companies are designed to do is they're designed to come up with these decision trees that are of incredible complexity to determine the best possible percentages of outcomes for you as an individual based on your attributes, like your age, the kind of car you drive, how long you've been driving, and so forth. That's how they make money. If they can come up with the best sort of classifications for you as an individual based on the attributes they can observe on you, then they can charge you just the right amount to make a profit, but also give you competitive rates so you're willing to go in with them. Speaking of big data, here is a big chart of monthly active users for Facebook, where this is in millions of users. We see that Facebook has something like 2 million monthly active users, or 2 billion monthly active users each quarter, which is pretty insane if you think about it. Companies like Facebook track millions of users every day. And to keep track of all this individual data points, databases are going to have to associate names with user information. We cannot expect as users these websites to operate slowly. Otherwise, we would just close the app and move on with our lives. Users expect instantaneous responses. We have observed two structures that have efficient lookup. The HashMap, which is O of 1, if we have a good hashing function, and the binary search tree, which is log of n lookup, if we can sort the data. If we're operating one of these super large companies and we're working on a ton of big data, then we are going to have to be very careful about our decisions when it comes to storing this user data so that we can retrieve it very quickly and also do it at scale. Enterprise databases, like MySQL, use something called B+ trees to store information in a compact yet efficient way. B+ trees are like binary search trees. On the left side, we find lower values. On the right side, we find bigger values relative to each other. We get something that resembles log of n lookup. But unlike binary search trees, a node can actually have any number of children rather than just 2 children. And these B trees are perfectly balanced. And part of the balancing act comes in during the insertion process. The clever thing about this is it's going to enable certain sequential data to be represented in the B tree, and the B tree is going to be sort of smart enough to compactly represent data together when there isn't really a meaningful amount of extra optimization you can do by adding additional layers into the B tree. You might be wondering now, we spent so much time learning about hash maps. Why not use those instead if we can get O of 1 lookup rather than this O of log of n lookup? There's 2 problems. The first is that there's no sequential ordering. We've seen how we can search binary search trees in a particular way to get them back in an ordered fashion. And B trees are actually designed to give you an ordered structure that has the same benefits as a binary search tree. But with hash maps, because the data is inherently randomly organized because of the random nature of the hashing function, we are going to have to store a supplemental structure if we want to maintain ordering for the key value pairs that are being stored inside. The second consequence of using hash maps is we waste quite a bit of space. We've seen how the load factor can dramatically adjust how much space is being wasted in the hash map versus how efficient the lookup of the hash map is. We can waste a ton of space to get more efficient lookup because we will have more buckets to spread our key value pairs across, or we can be more efficient in our space, but at the cost of possible bad performance because we're ending up storing several key value pairs together in the same bucket and having to perform a whole bunch of iteration. By using these kinds of B tree structures that are based on binary search trees, we can get this pretty consistent behavior and not have it be something that requires supplemental structures to keep track of ordering for us. Not that the hash map is a bad thing. HashMap strikes back. HashMap is used everywhere still. HashMap is excellent for dynamic content at a small scale. We can see hash maps everywhere, just how we want to associate data to other data. Mapping news articles to links, zip codes to cities, videos to thumbnails, users mapped to messages. Both JavaScript and Python as languages actually have hash maps as first-class citizens of the language because of this process. Every object inside JavaScript and Python is actually a hash map underneath. Whenever you do a property lookup on one of these languages, you're actually doing a sort of hash map lookup on the object itself. Let's see a concrete example of what I mean by that. Here is some valid code in both Python and JavaScript. You can define a hash map as being a new hash map just by these curly braces here. You can map a string to another value, like Seattle in Washington or Portland in Oregon. In JavaScript, we can perform property lookup on object types and treat their method signatures, their method names, as strings by invoking the same bracket notation that we saw with the hash map definition. So to invoke console.log, I could actually do console and then look up the string log property on console to get the method reference. Here's some valid code in Python. I can define a function foo that prints out hello, and then I can set a mapped value of thing and world on foo itself. So I can actually associate key and value pairs on a function definition, which is definitely a little weird because the function itself is not normally thought of as a hash map structure. But we indeed can do this. I can invoke the foo method on its own, or I can invoke getAttribute on the foo object that can retrieve the value associated with this thing key. Bonus round. Linked list as blockchain? Blockchain was the rage of yesteryear. You may have heard all the hype about Bitcoin and how it died down and how it bounced back again and over again. The way blockchain works is that it's going to compose a linked list of hashes of neighboring blocks, where the hashes are going to guarantee, so to speak, immutability of the chain of nodes. What happens in a blockchain is that every single node contains a list of transactions. So this is people sending money to each other. Then a whole bunch of computers are going to work very hard to come up with the hash of the block that is eventually going to be inserted into the chain to represent the canonical list of transactions for the entire blockchain. Then every time we finish computing the hash for a given block, we move on to creating another block. The clever thing about hashing is because remember how hashing data is supposed to be consistent and predictable? Based on the underlying state of the information, it should always hash the same value. Well, in the same sense, if we use a cryptographic hash on this block, then this block should not be modified in the future if we have a hash for it already. So if we have a hash in the blockchain ledger, so to speak, that validates this block's integrity, we can neither modify the hash because it would no longer be the same hash of the block, nor can we modify the block itself, the list of transactions, because then the hash would no longer be equal. So this is one of those sort of immutability guarantees that blockchain claims to have, which is you can neither modify either the list of transactions or the hash that maps to it, because the hash itself will be consistent based on this list of transactions. At what cost, though? The single transaction footprint of a Bitcoin transaction is equivalent to power consumption of an average US household over 22 days. And this is actually an old number and it continues to grow. This is kind of one of those ridiculous things about Bitcoin and blockchain as from a practical perspective, which is the amount of extra computational power we have to do in order to have this immutability guarantee. So while it's especially novel that it's perhaps harder to go back in time and cook the books, so to speak, in terms of transactions, there is also this sort of societal cost of us needing all this computational power to have trust in this collective system that, frankly, in my opinion, is not entirely necessary. We have credit card systems that process millions and billions of transactions per day, and these transactions are not costing this degree of power footprint that Bitcoin does. So while we do have this distributed system, it kind of punishes us in another way that I don't think is necessarily practical. There's this University of Cambridge site that has the Bitcoin electricity consumption index that shows how Bitcoin itself, the entire network, consumes more than the entire country of Chile, which is pretty insane if you think about it. Okay, that wraps up our tour of applications of data structures. I hope that by the end of this video, you've gained insight into how all these different structures belong in their applications in the real world. We've seen how certain structures have hidden benefits, like the array's great caching potential when it comes to their practical performance. And we can't just necessarily depend on the theoretical basis to decide on what structure to use. We've seen how we can decide on using two similar structures that serve similar purposes, like the binary search tree or the hash map, in order to accomplish similar goals, but at different sorts of scales. With this newfound knowledge that you have and deeper understanding on how these data structures are used, I hope to give you the power to think critically about what you will use in the future for your applications. In the context of something like a job interview or a project at a software development firm, you're going to have to make important decisions about how you organize your data, and it'll be important for you to discuss with your teammates and your interviewer the kinds of trade-offs that you'll be making here. Maybe you're willing to waste a whole bunch of space to get really fast lookup. Maybe you think the data should be super fast, and we should use something like an array because we get nice caching benefits. All of these are factors you should definitely consider on top of the theoretical guarantees we've already learned about, like with Big O, in order to make a well-informed decision and pick the best structure that's best suited for your problem. Okay, that's all I've got for today. Thank you so much for listening. I'll talk to you next time.